All right, guys, welcome to statistics for April 7th. Yesterday, we began talking about sampling distributions, our first time jumping into the unit, and today, we are going to take some of the theoretical, conceptual information we talked about in yesterday's video, and we are going to apply it to some actual numbers and an actual scenario. So yesterday, you may remember me talking about a coin flip scenario of sampling distributions. So we're going to go over that one today. I'm first, after I reset the camera here, first going to draw a normal distribution curve, because all sampling distributions are going to follow a normal distribution curve like this, just a law of nature. And what we are going to do is we are going to determine the sampling distribution for getting a heads on a flip of coins, or on a number of coin flips. So here's the idea. Let's say we are going to flip a coin 100 times, right? How many heads out of 100 should we get? Well, we know the accurate number for that is 50. Will we get 50 every time? No. We might get 55, or we might get 47, or whatever it may be. But we should, probability-wise, get 50. I think we can all agree that, just fact of the matter, we should get 50. That is what is called the true proportion. This is an important term, or at least one that we're going to be using. This is the true proportion. So when we're talking about some sort of statistical measure, if we know the actual expected value, that is the true proportion. So 50 in this case is the true proportion. So the mean, or the average, the center of our normal distribution is going to be 50. What this says is that if we were to conduct this experiment, an infinite number of times, right? Or heck, we can just say 1,000,000 if we want to deal with real numbers. Then the majority of times, more times than any other, we will end up with 50 heads in those 100 coin flips. Now, we do need to figure out a standard deviation for this, or standard deviation being our term for just a single sample, but in a sampling distribution, our sample variability, or our sampling error, is another term for it. Now, to do this, to determine what is reasonable for us to get, you know how a minute ago we said, well, we might get 47 or we might get 55. The sampling error, the sampling variability, tells us that kind of range of what to expect is normal in a sample. To find that, we take the square root of PQ over N. Now, I know that looks kind of weird, and it's a whole bunch of variables that we're not 100% sure what means. But here's what we're going to do. P is equal to the true proportion. Q is equal to 1 minus the true proportion, or 1 minus P. One way to think about this is P is kind of like a number of successes, or the number of times you expect to succeed in what's happening, right? Like if we're flipping that coin 100 times, then we expect a heads, or a success, to happen 50 times. That's the true proportion. Which actually makes me realize I wrote Q wrong. I'm sorry. Q is N minus P. Now you may be thinking, well, what is N? N is the number of trials, or the number of times you're doing this in the experiment. So if we expect to have 50 successes in this experiment, 50 times that we should flip heads, then out of the 100 tries, or the 100 trials specifically, we would take 100 minus those number of successes, and we would get the number of failures that we expect. That's what Q stands for, is the number of failures. So I'm going to write that kind of off to the side here. P is successes, Q is failures. So the number of successes, number of failures. So if this were some sort of a weighted coin, right? Like, I don't know if something like that exists, but let's say that if we would have expected we should get heads 30 times out of 50, then our P would be 30 and our Q, or 30 times out of 70, or 100, my bad. Then our Q would be 70, because to get between the successes and failures, we should make up the entire number of trials. Okay, so we're going to go ahead and plug this information in. So we have 50 successes we're expecting, the true proportion, Q being the number of failures, in this case 50, and then N being the number of trials, 100, then we can determine the sampling error. I'm going to plug this into the calculator here. So if we're plugging this in, then what we want to do is square root, and we want to open some parentheses to do the multiplying in the numerator. So 50 times 50 in the numerator, divided by 100. So you'll see all of this was put in underneath that square root, and then we made sure to use those parentheses, otherwise our order of operations could get messed up. And we get 5. That tells us our standard deviation here is 5. So that means we can, if we go out one standard deviation, or sampling error, sampling variability, I apologize, there's so many terms for effectively the same thing. We go out 2, that's another 5, up to 60, and then down to 40. So here's what would happen. We said yesterday that within one standard deviation is 68% of data. Within 2 standard deviations is 95% of data. So this tells us that in 100 coin flips, it is very likely that it is 95% likely that our sample will have between 40 and 60 heads. Now, if we were to get a smaller number or a larger number than, smaller than 40 or larger than 60, then that's unusual. That's atypical for us, right? This sampling distribution informs us what, or when, I guess I should say, we get an unusual number. So if you were to do this experiment and you would only end up with 35 heads, and you think to yourself, well, is that odd? Is that like a concerningly low number? Well, the sampling distribution says for you to get below 40, you got to be like, there's like less than 2.5% chance to get less than 40. It's a very, very low chance. Now, this seems relatively low impact in the world, talking about a coin flip, right? But we use this for bigger things. Yesterday I mentioned like some medical trials, right? So if we had a medical trial and we were charting how someone's, I don't know, like cholesterol, say, is supposed to fluctuate or change over time. If we know that in a typical person or a typical group of people, if you do this, then it's supposed to change in some way, 95% likely that it changes in this manner, then you'd say, okay, well, that's normal, that's reasonable, I'm within the realm of what's likely to happen. Maybe this new medication I'm trying isn't actually doing much for me because it's still within the range of what's normal. But if you get a number that's way off the charts, then you start to realize I didn't have data that fell within this normal accepted area of averages. And maybe this is something significant that we need to look at, right? So that's what this data is for. This sampling distribution is for, is to be able to tell us what is an expected outcome to a trial. Specifically here, 100 coin flips, and 95% of the times we ever do this experiment, we should end up between 40 and 60 heads, with the most times being at 50. If you have any questions about this, feel free to send me an email. There's no additional work today. As a reminder, we will not have a video for the rest of this week because of spring break. We will be back next Tuesday, and we'll be taking this sampling distribution information and putting it into practice again, probably with some of the actual questions on this packet. By the way, if you have not got that packet, if you didn't go pick it up from the school on pickup day, it is available on your Google Classroom. It was posted there on April 1st, so you can download a PDF of that. Again, if you have any questions, let me know. Otherwise, I'll see you guys next week.